This is the second video in a series of lectures on electromagnetic waves. In the last lecture, we introduced the wave equation, which we derived from Maxwell's equations, and in particular Maxwell's equations in the so-called source-free region, away from charges and currents, and particularly currents. We also derived the wave equation in a special form by assuming that the electric and magnetic fields have time harmonic dependence, that is, that they are sinusoidal functions of time. In this lecture, we're going to look at the solution to the wave equation and a special class of solution known as a plane wave. So we ended off last time by deriving the Helmholtz wave equations, which are shown here. For the electric field, we have this equation here, Laplacian plus k squared, all operating on E tilde, which is our phasor expression for the electric field, is equal to 0, and a similar expression for the magnetic field. So these are homogeneous differential equations as a function of spatial variables only. Again, the time dependence of E has been assumed so that we can replace our general electric field with a phasor, which we see here. And these phasors, E tilde and H tilde, are only functions of space. So we automatically know the time dependence because we've assumed it. And our goal now is to try to find solutions for E tilde and H tilde, which are only functions of space. So here is the vector wave equation or Helmholtz equation for the electric field. And it's instructive for us to look at solutions for the electric field because we can apply the same process to the corresponding equation for the magnetic field. So the first thing that's important to realize with these equations, this particular equation, and is actually a compact representation of three scalar equations, since it is a vector equation. It is an operator, del squared plus k squared, acting on a vector quantity, E, or in this case, E tilde. So let's write out the three scalar expressions that this actually corresponds to. We have Laplacian plus k squared. This is our operator in parentheses, and this acts on Ex, and the right-hand side should be 0. The same operator also acts on the y component of E, and the same for the z component of E tilde. Okay, so this is our compact expression on the top has now been split into three scalar equations. So we can solve for Ex, Ey, and Ez separately by looking at these equations. Next, let's expand the Laplacian operator. And for the types of solutions to the wave equation that we're going to be looking at, they're going to do this in Cartesian coordinates. So let's expand the Laplacian operator in Cartesian coordinates. So the Laplacian operator expands to a second derivative with respect to x, a second derivative with respect to y, a second derivative with respect to z, and these all act on E tilde, and then we can even absorb the multiplication by k squared into this operator here. And of course the result is still 0. We can basically write the exact same expressions for Ey and Ez. So let's just do that here for completeness. So there is the expression for Ey. Again, it can be solved with the first equation. And here's this final expression here for E tilde z. So this may seem like a daunting set of equations to solve initially, but it's a lot easier if we make some assumptions about the electric field that we're trying to solve for first. So let's make a few assumptions to help understand these equations a little bit better. So the first assumption that we'll do is to assume that the electric field E E only has one component. And let's say in this case that it has an X component. So we're going to assume that it doesn't have a Y component or a Z component. And that's a perfectly valid assumption. Our wave equation still holds under those circumstances. It's a very particular set of components for the electric field that we're deriving the solution for. So if we go to these three equations that we have on the right-hand side, we essentially don't need to solve for these two equations because we already know that there's a trivial solution for EY and EZ. So we're basically saying that EY and EZ are 0. So that means we only need to solve one of these three equations, which obviously simplifies things a great deal. Now, let's also assume something about the spatial dependence of the electric field. So what we can do is let's assume that the wave is uniform . So the solution is uniform in the Z equals constant plane. So what does that mean? That means that in any plane that's parallel to the XY axis, the electric field solution, EX tilde in this case, is uniform. That is, it does not change with X or Y, right? Because it is supposed to be constant in a plane that's parallel to the XY plane. So this means that the spatial derivative of the electric field component that we've assumed is non-zero, the one that we're concerned with here, EX, doesn't vary in the X direction. So if it doesn't vary in the X direction, its spatial derivative in the X direction should be 0. And similarly, if this field component doesn't vary in the Y direction, then the corresponding derivative in that direction should also be 0. So that simplifies things considerably further because now we can remove these two second derivative terms from the wave equation. So that leaves us with a very, very simple wave equation left to solve. Sorry, I crossed out d by dz, it should be d by dx squared. That leaves us with a very simple wave equation to solve for that remains. And let's highlight that with a box here. So this is essentially the equation that we want to solve. So this is second order differential equation in Z, and it's a homogeneous differential equation. We can rewrite it over here because now that we know that E tilde X doesn't depend on X or Y, our partial derivative actually becomes an ordinary derivative. So this is the equation that we want to solve. And in your earlier calculus courses, you've studied solutions to this, or you've derived solutions to this. This is what we call the wave equation. And we're going to write out the solutions down below. So we are arriving at a solution for E tilde X. We know that that solution is only going to depend on Z. Again, the time dependence of EX is already assumed, so we don't list it here. This is only the phasor part, the part that varies with space. And the solution to the wave equation that we wrote up above is actually the superposition of two complex exponentials. We know that exponentials are always candidate solutions for homogeneous differential equations, and this is no exception. So let's write the solution as the sum of two complex exponentials, as shown here. So the first term has a constant out in front, which I'm calling E naught super plus. And there's another constant in the second term, E naught super minus. So that whole thing is just a single constant. And then you can see our complex exponential solutions here. One term is e to the minus jkz, and the other term has e to the plus jkz. And if you're unsure that this is actually a solution to the wave equation, try substituting it in to the equation that we have up above here, and you'll find that this requirement that these terms basically go to 0 is satisfied. So this is a solution to the wave equation that we have, the particular wave equation that we have studied up above. The solution for E tilde x is our phasor domain solution for the x component of the electric field. So remember that the phasor only captures the spatial dependence of the field. The time dependence is built in to our time harmonic assumption for the solution. So if we want to physically interpret this solution to the equation that we wrote up above, it's instructive for us to write the corresponding equation that describes both the spatial dependence and the time dependence. So how did we do that? You'll recall that in general, if we want to write, for example, Ex as a function of space and time, we would need to take a phasor domain expression. For example, maybe we'll take the first term that we've in our equation above. Let's call that Ex tilde super plus. And we would take that phasor domain expression, it only depends on z, multiply by e to the j omega t, and then take the real part of the corresponding resulting solution, or the term, the product that we have here. So let's try that for this particular term here, which I called e tilde super plus for the x component, or ex tilde super plus. Let's substitute that in here. So we have the real part of E naught plus, and we'll multiply that second exponential term by e to the j omega t. So we're going to have e to the j omega t, and then we still have the leftover e to the minus j k z term. Let's merge these exponential terms into a single one. So this would be e to the j omega t minus k z in parentheses, as shown here. And now we can take the real part of this expression. It's useful for us to realize that this scalar out in front, E naught plus, itself could be a complex number. So it could have some magnitude, which would just show this way, and it may have some phase, which will indicate as phi super plus. Okay, so it has a magnitude term on the left, a phase term on the right. So let's substitute that in. Here's our magnitude term. And if I absorb the phase term into the expression, a single exponential term, we have e to the j omega t minus kz plus phi plus, shown here. Now we can take the real part of this. If we take the real part of the first term, well, the magnitude of E naught plus is a real number already. So we'll just write that as magnitude of E naught plus. And then when we take the real part of the e to the j omega t minus kz plus phi plus term, we realize that through Euler's identity, this would turn into cosine of omega t minus kz plus phi plus, and plus j sine omega t minus kz plus phi plus. And we don't care about the imaginary part, we're only keeping the real part here. So the real part that remains is cos omega t minus kz plus phi plus. So this is how our actual electric field component, Ex, varies with both z, which is our spatial variable, and time. Remember, Ex doesn't vary with x and y. We assume that it doesn't vary with x and y. So everywhere in an x equals and a z equals constant plane, you can see that this expression is constant, because if I hold kz constant in this expression, then at each instant in time, Ex is the same value regardless of the value of x or the value of y, because we don't see x or y as variables in this equation at all, right? So no matter what point in space I sample Ex, if I move along the x direction or along the y direction, this field appears uniform. So we have a name for this solution. This is called a plane wave. because it is uniform in a plane. So if I draw a plane here, and let's say that this is these are our, let's draw some axes here. So let's say that this is the z direction. So in order for this to be a right-handed coordinate system, this would have to be x and y. Well, no matter where I sample in the x or y plane, I get the same value if this is at time equals constant. Let's just pretend that time was a constant. I'm trying to evaluate the expression I have for ex. We see that everywhere I evaluate in this plane that's normal to the z direction, I only have an x component of the electric field, and it doesn't change with x and y. So if I was to draw little vectors on here, everywhere I sample along this plane, the electric field is pointed in the x direction, and the length of those vectors are all the same. The actual length would depend on what the value of omega t, kz, and phi plus happen to be at that point in time. So this is a plane wave, and another very important property of this plane wave is that it travels. And this is most obvious by looking at the second part of our solution here. This function, cos omega t minus kz plus phi plus, is a function of two variables, time and space. Now, for the moment, let's just look at the behavior of cos omega t minus kz, because we should recognize that adding a constant to omega t minus kz, which is what that phi plus does, isn't going to change the fundamental behavior of this function. It just shifts it left or right. So this function depends on both space and time. And if I'm trying to track a particular constant phase point on this, let's call omega t minus kz, let's call that v, right? Let's let v be equal to omega t minus kz. If I want to keep v constant, so if I plot a function of cosine function, so here's v, and here's cos of v. We know that cosine function looks something like this. And let's say I want to keep the value of cos v constant. So let's say I want to stand at this point on my wave. Remember that this function v is a function of both time and space. Now, time can only move in one direction, upward. So once I start time going, t is always an increasing variable, right? So the product omega t is going to be increasing with time. So if I think about what happens to this wave, if I want to remain at this fixed point on this wave as time increases, I basically want to keep v constant, right? Because this is some particular value, let's call it v naught, and I'm trying to stay at this very particular position of my wave, which is cos v naught. Well, in order to stay at this position, cos v naught, I need v naught to be constant. If time is increasing, then z is going to have to increase in order to keep the argument to the cosine, which is v, constant, or equal to that constant v naught. So that means that this point, this constant phase point where I'm standing here, is going to move to the right. This wave travels because z has to increase, or in order, this is not a plot versus z, but in order for v to remain constant, if omega t increases, the product kz will have to increase by a corresponding amount to keep the difference between omega t and kz constant and equal to this value v naught. So this is explained with this more elaborate plot here that I have for ex, which is again a function of both space and time. And it's that particular term that we were looking at on the previous slide. I guess we were calling this E naught plus, and this would be the magnitude, and we've dropped the phase term phi plus here just for simplicity. Well, consider what happens when we plot this function as a function of space, z, for various instants of time. So first, we plot it for time equals t naught, which is this blue curve here. Then, if time increases to t1, which is larger than t naught, this purple curve is the one that results. And if I consider another time instant t2, which is larger than the previous one, t1, I get this curve here. If you look at these three curves, this wave looks like it is traveling to the right, or in the positive z direction. So previously we were on a previous slide, we were looking at a constant phase point. Let's say I was riding the wave at this point before, and I'm trying to stay at this particular value of the this particular phase point on my cosine curve. Well, if I increase time and I want to remain on that exact same point over here, time has increased, and therefore kz has had to also increase so that omega t minus kz is equal to the same value, which we were calling u naught, or v naught, sorry, in the previous slide. So clearly my position has changed such that instead of being at z naught, I'm now at z1, and z1 is larger than z naught. I've moved to the right. I've moved in the plus z direction. So this equation that we wrote here for Ex, this plane wave solution here, this is a wave traveling in the plus z direction. And that is why originally I put this these superscripts here plus, because recognize that this particular solution to the wave equation travels in the plus z direction as time increases. So if we go back to our original phasor domain expression here, this is a wave traveling in the plus z direction. And if we repeated this analysis for this term here, this is a wave traveling in the minus z direction, right? There's no reason why our wave equation should differentiate between one solution or the other. They're both equally valid, and we recognize that even the amplitudes of each solutions could be different. And in fact, we don't know the answers for E naught plus and E naught minus until we establish some more sort of boundary conditions on this problem. And that's not what we're going to focus on at the moment. At the moment, we want to recognize that these are two ways that we recognize the ways in which we write waves that travel in particular directions. So the first term that's been circled in this red equation travels in the plus z direction. We know that by taking that term and substituting it into our expression here to turn a phasor back into a real-time expression, we arrive at an expression down here that clearly illustrates the wave is traveling in the plus z direction. And if we took that second term up above, this one, and subjected it to the same process, we would end up with a wave that is also uniform in this plane that we've sketched on the right here, but travels in the opposite direction, in the minus z direction. Think about what would happen if we had put a plus here instead of a minus sign. Then as time increases, I would need kz to decrease in order to keep this term omega t plus kz plus phi naught plus equal to some constant. So these are traveling waves that are uniform in a plane normal to the z direction.